All right, so we looked at, after the quiz, right, we started looking at dependent and independent events. Well, actually, you know what, before, let me see, I want to do, this one here. So this is a different question. So this is on page 48. Sorry, it's just a page before. So it's an example here. There are 4 roads to travel from Albonzo to Bethany. 4 roads and 3 roads to travel from Bethany to Cartwright. How many different ways can someone travel from Albonzo to Cartwright if you only use each road once? So, anyone, how many different roads? There's 4 roads to travel from Albonzo to Bethany, and 3 roads to travel from Bethany to Cartwright, right? So we have, we're going from A to B to C, right? So just using the first letter, right? We have 4 roads and 3 roads. So, and we're going from, how many ways can we get from A to C? 12. Yeah, it's just an outcomes problem, right? So outcomes. So again, instead of asking, right, instead of giving you choices of things to put on your pizza, right, I'm giving you roads to travel, right? So it's 4 times 3 equals 12 ways. But now let's do so we can do a table or we can do an outcome tree, right? Let's do a tree. Maybe we'll do both. Let's do a tree here, right? So we can go, so we start at Albonzo and we have 4 roads to travel to Bethany, right? So one, let's give myself a little more space here. 1, 2, 3, 4. Right, and then, so now right, so we have 4 different ways to get to Bethany, and then now we have 3 different ways to get to Cartwright, right? So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So you don't have to like label, I'm labeling them A, B, and C for the first letter, so where we're at in terms of the cities. Right, so this is one option, right? Also, it's in orange as well, that is one option, right? So I can take the same road from A to B, but a different one from B to C, right? Or I can just take a different road from A to B all together, right? Or I can go from here, and let's say now I take that road from, right? So that is a route I can take. So your end results, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So 12 total routes. So this is kind of an example where a outcome tree may be a little more useful instead of an outcome table. Right, and again, if we wanted to do a table, let's call this, right, from A to B, and this is the roads from B to C. Now we're not given like what the outcomes are. Like when we're rolling a dice, we roll a 1, a 2, a 3. But in this case, we're just given roads, general roads. So you can label the outcomes any way you want. Right, so what I'm going to do, I could just do again, you can do anything you want, or you can just label them 1, 2, 3. 1, 2, 3. Right, so there's how many roads from A to B? There's 4. Just label them 1, 2, 3, 4. How many roads from B to C? 3. So 1, 2, 3. Right, and then you can just do, we take road 1 and then road 1, road 1, road 2, road 1, road 3, road 1, road 4. 2, 1, 2, 2, 2, 3, 2, 4. Oops. Or we can take road 3 and then take 4 different ones. So road 3 and 2, road 3 and 3, and road 3 and 4. So I just decided to label the roads 1, 2, and 3. But just make note that I'm not rolling a dice here, right? So these numbers are just labeling the roads, right? Road 1, road 2, road 3, or road 4. I can take either or from A to B. And then I can take either road 1, road 2, or road 3 from B to C. So again, both give you the same information. Question? Okay. All right, so most of these I always ask, so you can always calculate how many outcomes you're going to get, right? We calculated that first. We have 12. So if I do ask you to do a tree or a table, you should end up at the end of your tree should be 12 branches, or in your outcome table there should be 12 different boxes or outcomes. Any questions? Sorry? Oh, you need this? Yeah, no problem. So again, make sure you know how to do a tree and a table. Yeah. So I'm hoping to cover the last topic today. Okay. Right, and then we went to dependent and independent events. And again, essentially nothing really new here. We're just now dealing with, okay, well, we can have a scenario where we take something out of the sample, or take something out of our possible number of outcomes and not replace it. So we can take the card out of a deck and not replace it, or we can roll a dice, or not roll a dice, but maybe take a marble out of a bag and not replace it, right? And then calculate the probability of how that affects our second draw of a marble or our third draw. So we calculated these, right? And for independent events, right? So whenever we take something and replace it, it's when we take something again. So in this case, we're drawing marbles out of a bag. We take a marble out, record the result, and return it. It's not going to affect our second draw because we essentially just took it out, recorded, and returned it. So we're grabbing from the same amount as before and the same distribution of colors. So nothing changes, right? The total possible outcomes remains the same. But for dependent events, so if I take a marble out and don't replace it, so dependent events, right? That means we don't replace. So you can always think whenever you see no replacement, that means dependent events, right? So when we take a marble out and don't replace it, our second draw that we take out of the second marble that we take is going to depend on our first marble that we take. So our outcomes will change. So for here, right, we took a marble out and didn't replace it. So now we only have 9 remaining. And then we got to make sure that the marble that we took out, was it a color that, so I'm asking the probability of drawing a red marble next. Well, there's still, right, we took a blue one out and didn't take it and didn't replace it. So now there's still 3. So it's still 3 over 9. But if I take a blue marble out and don't replace it and want to know the probability of drawing another one, so my outcome is different, my number of outcomes, because I took a marble out and didn't replace it, so now I have 9. And now for the probability of the next one being a blue, well, I took one out and didn't replace it, so now I have 4 blue marbles left, so it'd be 4 over 9. So again, nothing really new here, still calculating probabilities, just different scenarios. All right, so that was an example with drawing marbles from a bag. And then we went through another example, again, of just drawing decks or drawing cards from a deck. Right, so there's a lot of examples here. Right, so the probability of a red face card if the first card was a red jack. Right, so let's calculate so let's review here, right? So for all of these, Julia's drawing a card from a standard deck of cards without replacing it and then drawing another card. So without replacement. So all of these questions are without replacement, so they're dependent. So she takes a red face card, and then, she takes the first card as a red jack, and now what we want is the probability of the second card being a red face card. Well, she took a red jack, so there were 12, right? Again, there's 52 cards in total. We took one out, so now there's 51 remaining. Probability of a red face card. Well, how many red face cards are there? 6. Yeah. There's 6 red face cards. Was the first one a red face card? Yes. So then we have 5. So then our probability of drawing a red face card is 5 over 51. Right, so the probability of an ace. Right, so for all of these, we're taking a card out and not replacing it. So our total is going to be 51. The first card was a king of diamonds. Now we want the probability of an ace. Well, there's 4 aces remaining still, because the first card wasn't an ace. So probability of an ace, the second one being an ace, is 4 over 51. Right, if the first card's a queen of clubs and we want the probability of drawing a queen, right? Well, we had 4 queens. We took the queen of clubs away. So now we have 3 queens left. So the probability of drawing a queen is 3 out of 51. Right, so this one's very similar. Sean drew a card from a standard deck of playing cards. It was a face card. He did not put the card back in the deck, so we're dealing with dependent events. What is the probability that the second card drawn will be an ace? Well, he took one out and didn't replace it, so we have 51 remaining cards. He took a face card out, and we want the probability of there being an ace, right? So there's 4 aces still remaining. The probability of an ace is 4 over 51. So similar, same scenario as part F there. So now, if I wanted the odds, what would be the odds of the second? So what would be the odds of the second card being a red face card? I have the probability, so now I just have to convert this probability to odds, right? So the odds would be, sorry, so 5, right? And then this is our total, so we have 51 cards remaining. And these two numbers should add to our total, 51. So this one can't be 51. It's 50, but if we wanted to add to 51, it's 51 minus 5. So the odds would be 5 to 47, 48, no, 46. 5 to 46 would be the odds of the second card being a red face card. Right? And then for this one, it would be 4 to 51 minus 4. So it would be 4 to 47. And this one would be 3 to 51 minus 3. So 3 to 48. Right, so really this unit boils down to probability and odds. And just knowing how to split between them. Other than that, it's just kind of different scenarios, questions that I can ask you. There's obviously predictions as well and stuff like that. Yeah. Yeah. So it's super important to understand, right? Probability and odds, and making sure when I'm asking for odds, you give me odds, and when I'm asking for probability, you give me probability. Because I hate taking, because I know some of you just misread the question, gave me probability when you're supposed to give me odds, but I know that you know how to give me odds because you did it in a previous question. But there's marks allocated to that, so just make sure you read the question. Okay. And now there's plenty of examples here. So I'll give you some time to do this example here, and I'll give you a couple minutes, and then I'll check back. We'll go through it, and then we'll start and go through an example of our last concept. Yes. answers, right? So part A was just a normal, so we were given 5 red, 12 blue, 18 white beads, right? And the first one was just the probability of drawing a white. So it's just a regular probability question, right? So we have 15 white beads that we can choose from and 45 total. Oh, it's supposed to be an 8, not a 5. 18 over 45. Sorry, you have 18 white, not 15. Right, so now the first bead drawn is a white. It's not replaced. What is the probability that the second one is also a white? Right, so it's not replaced, so your total always changes when you're dealing with no replacement. Right, so you had 45 in the bag, you took 1 away, so now you have 44 total. And now we want to see what is the question asking? The second one being a white. Well, the first one was a white, right? So we had 18, and we took 1 away and didn't replace it. Now we only have 17 white to choose from. So it's 17 over 44. For part C, right, first bead drawn was also was a white again, not replaced. But now we want to know the probability that the second bead drawn is a blue. Right, so again, we drew a bead and didn't replace it, so our total changes to 44, not 45. And then probability of blue, well, we drew a white, didn't replace it, so we still have 12. We still have 12 blue remaining. We didn't take any blue out, so it's just 12. We still have 12 blue remaining in the bag, but we have a total of 44 now. And for part D, right, from the original bag, so it's just re-giving the information for the original bag. A white bead and a blue bead were drawn and not replaced. What is the probability that the third bead drawn will be a red? Well, first, right, the total changes always, right? So we took 2 beads away from our total, so now we only have 43 beads. The first bead was a blue, the second bead was, the first 2 were white and blue. We want the probability of a red. Well, we didn't take any red out, so we still have 15. So it's just 15 over 43, our new total. Any questions on replacement, not replacement? Okay, so I'm gonna skip through quite a few pages here of just practice questions because I want to go over the last concept so I'm skipping all the way to page 69, right? So this is our last concept. I just want to get this out of the way so that you have it, and for the weekend, you've seen an example, and this one is a little bit, there's some new stuff going on here, there's new formula. So expected value, we have something called expected value is an application of probability that involves the likelihood of a gain or a loss. And it is stated as a dollar amount. Right? So, right, it can be used in insurance, business, likelihood of winning or not, like gaining money and not gaining money. So like in investments and wealth, so there's a lot of things that expected value could be used for in real life. So it's only accurate in the long run. So after playing a game many times, and that again is very common in not only probability but statistics, right? We always want statistics, probability. We're always looking at the long run, right? And we always to increase accuracy, we always want to increase our sample size, right? So whenever you're doing a survey and you want to get a good representation of a population, right? So if Winnipeg wants to get a good representation of what the city Winnipeggers view, whatever their survey is on, right? They want to survey a good amount of people from different areas of the city to get a good representation of the whole city, not just 10 people from Sisler, because that wouldn't be a good representation of what the whole city thinks. But anyway, right, so you need a large sample size. The formula is the notation is just EV, short for expected value. The probability of winning. So it depends on how many different scenarios we have, right? So the probability of winning once times multiplied by the prize that we win minus the cost of playing, right? Plus the probability of winning again times the prize minus the cost again. So, and then we continue all the way until the last term is we're minusing the probability of that we lose times just the cost. Right, so we'll do an example to see how this formula works. Right, but you have to look at the sign to make, so you may have to look at the sign to determine what it tells you. Right, so expected value can be positive, 0, or negative. So it's different from probability. So I forgot to mention this when I was going over the quiz. Important thing about probability is always between 0 and 1 for decimals, or fractions. So 0 and 1, or 0 and 100% for percentages. Right. So some of you were calculating probabilities that were not between 0 and 1. Right. So what I would do just for that, a good test kind of tip, I would say, is just that I kind of learned in university, is if you don't know, if you know that your answer is wrong, but you don't know how to fix it, just say like, so for example, you got a probability that's greater than 2, just say, or that's greater than 1, and say you got 2. Just say, I know this is wrong because it's greater than 1. So I know that you know it's wrong, right? Because then when I'm looking at it, I'm just assuming that, oh, you thought the probability was actually 2. So that kind of just helps me when marking as well, right? I knew that you got it wrong, but you just didn't maybe know how to fix it, or you're going to come back to it and you didn't have time. So just a good test tip. If you know your answer is wrong, and you want to keep the work, because it's always good to show your work as well, so I can see as well. So expected value can be positive or negative. So if it's positive, that means we expect a gain. So it's a good idea to either play the game or invest. If it's 0, it's fair play. It's a fair game. So there's kind of, you can think of it as equal odds. And if it's negative, you expect loss is expected, right? So it's generally a bad idea to play the game or invest, depending on the context that we're talking about. So the value calculated for expected value is the average amount you are expected to gain, lose per game or bid, right? So it's the average amount that you gain or lose during a game. Right, and it's always true in the long run, right? So we want as many. It does not work if you only play a couple of times. So let's see an example of this. So a game at a summer fair consists of drawing marbles from a bag. The bag contains 10 red marbles, 30 yellow marbles, and 60 white marbles. So, and now it gives us a scenario. So if you draw a red marble, you win $25. If you draw a yellow marble, you win $7. And if you draw a white marble, you get nothing. And it costs $3 to play. Calculate the expected value of each game. Right, so if we look back at our formula here, we have a total. So how many marbles do we have in total? Right, so we have 10, 30. So we have a total of 10 plus 30 plus 60 equals 100 marbles. So our expected value, right? So again, our formula here is the probability of winning times the prize minus the cost, right? So winning, so we have winning 1, winning 2. So in this case, we have, right? If we draw a red marble, we win $25. And if we draw a yellow marble, we win $7. So those are two different, right? Two different terms in our expected value. So the probability, right, of winning times the prize, so it's $25, right? Minus the cost, which is $3. So that's if we draw a red marble, right? Plus the probability, we can also win $7. Times the prize minus the cost. Or sorry, the prize minus the cost, yes. And then now for this one here, if you draw a white marble, you get nothing. Right? So plus the probability of losing. So the probability of losing is just the probability of drawing a white marble. So this is actually, right? So our last term here, right? So we're adding all the different ways we can win, and then we minus the way we lose, right? So make sure you note that minus there, right? So it's minus probability that we lose times the cost, right? Which is $3. So the probability of winning $25, well, that's the same, right? If we draw a red marble, we win $25. So how many ways can we draw a red marble? So there's 10. I'm just going to draw out. There's a lot of things going on, so I'm just going to draw it out step by step. So there's 10 red marbles. And we have 100 total, right? So that's times 25 minus 3, right? So that's just $22. Plus the probability that we win $7, right? So that's, I don't like how I wrote that out, but I'll just, so it's the number of the number of yellow marbles, because if we draw a yellow marble, we win $7. So it's the number of yellow over total times 7 minus 3, so that's just $4. Then minus the probability that we lose. Well, how do we lose? We lose if we draw a white marble. So it's the number of white marbles over our total, which is 100, times the cost of $3. Right? So it's 10 over 100 times 22. plus the number of yellow, right, which is 30 over 100 times 4 minus 60 over 100 times 3. Any questions how I set this up, set the equation up, and like plug everything where everything went? Okay. Right, because we're just saying we win $25, right? This is equivalent to just the probability of drawing a red marble out of the bag, right? So now we just plug it into our calculator here. Right, so we have 10 over 100 times 22, right? So that's 2.2 plus 30 over 100 times 4, right? So that's 1.20, and then minus 60. Sorry, I'm not showing you what I'm typing. 60 divided by 100. Oops. Times our cost, which was 3. So minus 1.80. Yeah, sorry. Right, so, and, right, it is stated as a dollar amount, right up here. Stated as a dollar amount. So our answer is 2.2 plus 1.2 minus 1.8. So our expected value is $1.60. So we are expected, right? So it's positive. So it's a relatively good idea to play the game. But that doesn't mean if you, again, it's over a long period of time, right? So just playing it once, right? It's maybe not a good idea, but it's over a long period of time. That's our expected value. So should you play this game, justify referring to the answer in A. Right, so since the expected value, right, equals $1.60, right, is positive, we expect to gain, right, win money in the long run. Oh. So since the expected value is positive, we expect to gain money in the long run, right? So yeah, it's not. So we should play the game. If you were to play the game 125 times, how much would you expect to win or lose? right? So now we want to predict if we played it 125 times, how much would we expect to win / lose? Uh,
Can you just say something about there, guys?
yeah.
Should you play this game on the exam? It doesn't matter what the number is. If it's positive, play. If it's negative, you shouldn't play. All right? That's so. Let's say you get it all wrong in A. If you answer B correctly based on A, you still get the mark. So always remember, don't leave it blank. Like, give it a try, calculate something, and then answer B based on what A was for you.
There's only a couple minutes left. So so essentially those are all the concepts. I don't want to so I don't want the bell to ring on us here. How much would you expect to win / lose? So the probability of winning times 120. So it'd be a prediction question. But the probability of winning would be, right, so we'd have to calculate that. But I can post the, I can finish off this this question, and I will post it. And for the, so the rest of the book is just questions, right? So even here, right, it looks like new material, but it's just a review, right? So it's just a probability of dependent and independent events, converting between odds and probability, right? So the rest, all the other questions that you haven't done, you can do, right? But I would recommend going through, right? Make sure you review obviously stuff that you didn't do well on the quiz. I know we didn't get, so you've seen expected value, we went through part of an example. I would encourage you to try like up to 72 maybe for expected value, and I can post the solutions. But other than that, right, it's kind of up to you now. There's a lot of questions in here that we didn't do as examples. So it's kind of up to you, right? If you know how to do, if you're comfortable with conversions, right? Don't keep doing conversions over and over and over again. Kind of look at your quiz, see what you need to work on, and kind of go from there. All right, and then so Monday we review. So if you have any questions, come like prepared with like maybe if you want to write down a list of questions as you go through that you didn't understand that you want me to go through in class. We can do that. I can also just have some stuff prepared as well, but I want to go over obviously what you need to review. So Monday will be review and then test on Tuesday. Have a good weekend.
Good weekend, guys. Short week next week. Friday. Two Fridays back to back.